Okay, so for this problem, we are going to be looking at these smooth spheres with drag coefficient that are entailed with some experimental data that we are given. And so for this first part of the problem, we are going to be wanting to create a log graph for our drag coefficient as a function of our Reynolds number. So let's begin coding here. First, I want to import my numpy as np, and from our scipy dot integrate, we're going to import our IVP solver. And then we are also going to be creating a graph, so we want to get in our subplot maker. Okay, so that's running well. So now we want to define our function, and that function is going to be for our drag coefficient. Let me call it ED as a function of our Reynolds number. So I'll call that RE. And now we're going to want to start plugging in our experimental data. So I'm going to pull that up here, and we can see that our first equation will be A equals our Reynolds number over 5. And for our second, I'm just going to copy this in. And our final is our drag coefficient. But this is actually this is not experimental data. This is what we want to return actually from our function here. So we'll return this number that's produced right here. So we'll run that code, everything runs well, and we'll move on to the next portion. Okay, so now what we want to do is actually start defining our two axes. So we'll have an x-axis that will be in log space for 1, 7, and 500, or 1, 500, and 7. And then we will have our y value, which I'm going to call our ED underscore vals. That's what I'm going to define it as. And that is going to be equal to our ED of x, our function. Okay, something to note, my coefficient here is C. Sorry, I had it as E, so I just changed that for all those. And I had this as 1,507 and had it 1,7,500 is what it was supposed to be at. Okay, so now we want to move on, and we actually want to make our figure, right? So let's define that. So this is why we needed to add our subplot maker over here. And now we want what? We want a scatter plot, right? Big dot add underscore scatter, right? And then we want to start plugging in basically what our scatter plot's going to look like. So what we have is our x value. X value is going to be, well, x equals x. And then our y value is going to equal our CD vals that we defined earlier. So like that. And then our mode is going to be equal to lines. Okay, now we'll move on and start getting into some other things for the graph. Okay, so we almost have our plot, but we need to start adding some other things into. We need to start updating our plot a bit. So fig.update underscore x-axis. So one of the things we need for this is we need to specify our type. Since this is not just some average graph, we need to make this a log graph, or else once we plot it, it's not going to register that it's a log graph, and that's going to give us all sorts of problems. So we want that for both of our axes, since it's a log graph. And then the last thing we need to update is our layout or our dimensions. So fig.update layout, and then we do log here. Hold on, I think I have one thing wrong with my code, so I'm gonna come back. Okay, so I found what I was looking at wrong here. So I forgot that I need to put these into italics here. So just syntax error. And this is not a log, sorry. What I'm trying to define here in my layout is actually the width and height of our graph. So I'm going to set that to be our width to be 800, and we'll say our height is 600. Then we can also set our template to be a dark graph. So that should run. And then we'll get onto actually plotting the graph. Okay, so I had a couple things I forgot to add here. So my C value, that was one of the conditions that we were given that I just forgot to add. And then all of this was on the wrong line here. And then I also had this as axes instead of axes. So we got our plot here, and we want to look at just our question again. So we're asked to explain the steep drop in our graph that we can see here, where the Reynolds number is 300,000. So let's go back to our graph. And we can see that right here. Yeah, so that drop right there, so we have our sphere, and there it has different flow going around it. And it starts out with laminar to turbulent flow. So there's some boundary condition between those two flow types. So when you're simulating it on a code or on a computer, it really just simulates that boundary condition, that change between our laminar and our turbulent flow as this big drop here before it levels out again. So that's basically what we have here in our graph. Okay, so for this next problem, we are going to be taking that sphere, that soccer ball, and we're going to be kicking it at a 30-degree angle at 70 miles per hour, and determining where it's going to land and bounce first at. So we want to start defining a couple variables that we need for this problem. So first of all, we're going to have a starting position, right? So our X position is, we're just going to call that 0, just to make it simple. Let's say that the point that our ball is starting at is at 0.0. So then we also have a Y position, right? And our ball is not in the air yet, so we're going to call that 0 as well. And then we also have an initial velocity, so I'm going to call that V naught, and that's going to be 70 miles per hour. But we do not want this in miles per hour. We want it in meters per second, since that's really what we always do. We always use meters in seconds, and so we'll just multiply that by 1610 over 3,600 since there is 1610 meters in a mile and 3,600 seconds in an hour, right? So next we are going to be starting out with an angle, right? An angle that we start out with that we're kicking our ball at. And that angle we said is specified as 30 degrees. So we'll have 30, right? But we don't want that in degrees. Once again, we're going to have to change the units, and we're going to change that to radians, right? So mp.pi over 180. Okay, and so now we can actually split our velocity into its components, which we'll just call that Vx naught. And that's going to be our V naught times what? Times mp dot cosine, right? Cosine for our x value of theta. Theta, here we go. Okay, and then we have obviously our Vy, just be the same thing, except for sine. I can type it right. Okay. So now we're going to want to define our function next, but I'm going to move on to that in a bit. Okay, so now what we have next is we actually have to have our equations here, which I have pulled up for each of these velocities and positions of where our ball is going to be at, right? So I have them here along with some variables that we're going to need. So now we need to find these equations. We have some differential equations, right? So let's define those. So we'll just say the right-hand side of this first equation is, or the right-hand side of our equations that were our differential equations are going to be defined in terms of t, right? Since all of them are over dt, which is our time. And then we're going to call the next variable our vec, because that's going to be varying depending on which component we're taking. So I'm just going to lay these out in the form that I have here on my notes here. So I have Vx first, then Vy, then Px, our position x, and our position y. And that's all going to equal our vec, right? Okay, so now we want to define our Reynolds number, right? So Reynolds number, we know that that's going to be rho times V times, rho VD over mu. So we can see that we actually do not have our rho, or we have a couple of these variables that are not defined. So I'll get to that in a bit. But first, we're also going to want to return, or we're also going to want to put in our equation for one of our other variables. Okay, sorry, yeah, we need our force, right? So our force is going to be our CD, which is a function of our Reynolds number, right? Times D times rho times our V squared. And that's all going to be over 2. Okay, so yeah, I need to start defining a couple more of my variables, right? Since I don't want to do that. I didn't totally define everything here. So let's just begin. Let's begin with our rho. So our density, just for air, we need, I have it written down here, 1.2. And that's going to be in terms of kilograms per meter cubed. And then we have our viscosity. Viscosity will be 1.8 e to e negative 5 there. And sorry, Pascal seconds. And then we have our D, so our diameter. And for a soccer ball, we're going to say that's 0.22, meters. And then our mass of the soccer ball is just going to be 0.31. Okay, kilograms. All right, so that all looks good. And then we'll move on to the next part. Okay, so one more variable I forgot to define here. That is going to be our A, our area. So what's that? MP dot pi, right? Pi times d squared over 4, right? For a ball or a sphere. And then we also need to define we have a velocity here, so I forgot to put that in, but that's actually its own separate equation. Since we have it broken up into its components down here, we can actually just make it that value of our total velocity, I guess. So what's that? That's our components, which is Vx theta squared plus our Vy squared theta. The square root of those will give us our velocity, right? All right, so now let's start returning our values. So first we need our gravity. So what are we trying to return here? We're trying to return the right side of our equations that I have pulled up here. So let's begin doing that. So our first one is going to be the negative of our force over our mass. And then that times, put these in parentheses, make sure everything looks right. Times our Vx over our mass. Okay, so that's our first right-hand side. And then next we will have our negative gravity. And that will be subtracted by force over mass. And that will be multiplied by our Vy over our mass. Okay, so that's our second right-hand side. And then the next ones are just for our position. So we just know that's just our X and Y velocities, right? Okay, so now that we have all that, we'll move on to our time portion. Okay, so now we need to actually start specifying like our time that we're running our simulation for, right? So let's call that 10 for 10 seconds, right? Okay, and then now we want to actually we need to solve for our initial value problem, right? That's the whole reason why we put in the solver. So it's solve underscore IVP, right? And that will be for our right-hand side. And what will that be from 0 to 10? And that looks right. Then we need to specify our velocity, our x. We have all these variables, velocity, our y, initial, position x, position y. And that we need to also put in dense output equals true. We just need to specify that. Equals true, right? Okay, so that all looks right. Seems we have a problem here. So I'm just gonna fix that real quick. Okay, so I had just a bit of a problem with my V over here. It's just uppercase and lowercase was mixed up. So we'll move on. And so now we want to actually start plotting, right? So T plot, I'm gonna define. 0 to 10. And okay, and so now we want to specify our plots for each one of these variables that we have. And that's going to equal our solve dot res for our T plot. And now we'll keep moving on. Okay, so now let's actually begin plotting. So we're going to call this next plot, we're going to call it fig2 since we already have fig2 up there previously in our code. So let's make that. So make underscore subplots, right? Make that. Okay, so now that we have that, we want to make it a scatter plot, right? So fig2 dot add underscore scatter, and what our x value is going to be is we want that to be our position x plot, and our y will be our position y plot. And then what else do we need? We need our mode, and our mode is actually just going to be markers. So I think it's just marker, maybe markers. I don't know. I think it's markers, but nevertheless, that's going to be for this plot, since we are going to have 100 markers on our plot instead of just having a straight line. And so now we need to update our plot. So I'm just gonna drag this because this will just save me some time. And take that down here, add that right there, and change this to fig2, right? Okay, so let's run that and see how that works. So we have a problem somewhere. I'm going to, oh, yeah, I'm gonna figure that out and then I'll be back. Okay, so now that we have our plot, we actually want it to end when the ball hits the ground, right? So it's going under the ground right now. So we're gonna want to add we're gonna want to define another function here, hit ground for time, and in fact, same thing. And we want it to return it when want to return that. Okay. Okay, so now we need to define when the ball hits the ground, right? So hit ground dot terminal equals true. And we also want the graph to stop when it starts going negative, right? So when the direction goes to -1, that means that the graph's coming down, and we want it to stop when that comes, or once that happens, once it hits the ground, and then once it goes down, then we want to stop, right? Okay, so next we want to actually put that event in, right? So events equals hit underscore ground, right? So now it's actually going to register hit underscore ground is defined here. Sorry, we need to run that. There we go. Okay, so now that that has that's running, let's actually give me res here. So now we can see that our T events is right here, right? But we actually want to grab that. So let's do 0 and 0, since that's where we can grab it from. There's a problem here, but I'll be right back. Okay, so I see where I went wrong here. rs.t underscore events is what we wanted to grab, right? So we run this and we see T events right here. It's giving us 0. That's not correct. So we need to go back to that. Okay, so I just saw that I did not put in direction. It just said direct. So now it ran it and we get this number. So this is where our ball is going to hit the ground. So now we need to grab this little piece of code right here. And we want to put it right here since that's where it'll stop it. So now that we have that in there, we can run this. And there you go. That's where our ball, you can see the ball goes up, arcs, and then falls down. And this is where it's going to land. And that's the coordinates of where it's at.